Okay, good morning, everyone. Thank you for coming to the session. I'm more than happy that you're attending this buzzword-driven talk this morning. There's a couple of really nice sessions now at 10:30, so you can still reconsider and go to the other one. Okay, so let me introduce myself. My name is Bujok. I used to work for SBB in Bern in Switzerland. You can find me on Twitter under @TomBujok, and new followers appreciate it. You can also visit my blog, refistio.org, when you can read some more stuff about the project and open source project that I'm doing. You can probably know me from two ventures. I'm the author or co-author of the Baboon framework or shell for Windows. I'm also the co-founder of the No Fluff Jobs IT job portal, where we try to remove all the stuff, all the fluff from the IT recruitment. Okie dokie. So it's going to be yet another NoSQL talk, right? There's been so many things being said about NoSQL. This is a world of benchmarks, of tutorials, of certifications, of conference talk, or even separate conferences. I mean, if you type NoSQL in Google, there's going to be a salesman that will call you, even though you didn't give any number. I don't know where they find them, but still. So, in this world full of buzzwords and in this world full of, all the stuff that's really happening behind the scenes, it's really, really easy to lose the focus. It's really easy to get the gist of why we actually need NoSQL and what it actually can give us and what are the core design principles behind NoSQL. Because, I know that I can configure product X with product Y this way, and that I can handle 5 million of transactions of requests per second. But what is the core reason why I actually need it? So this is the thing that we want to cover during this talk. It's not going to be a detailed talk. So if you are a MongoDB expert and you have 100 nodes somewhere and sharding and stuff like this, and you have some latency problems, and you want to ask me the question how to solve it. A, I probably don't know it, and B, this is not the right talk for you. So we're going to really stay on the high level and try not to go really deeply into such details. So as you probably know, there's this big buzzword of big data. And why is it actually happening right now? So the way we are using the internet has changed rapidly in the last years. So in the beginning of 2000 or somewhere between 2000, 2005, 2006, we were mainly consuming the data. So we were reading some blog posts, we were reading some websites, we were basically consuming what's there. But now it has changed. In the era of Twitter, of Facebook, of Google+, and Instagram, and all the other portals, we are producing a lot of data. I don't know if you have seen this picture. It was taken during the Pope elections in 2005 and 2013, and the person who can spot the difference will get the first mug. So, yeah, as you can see, they all are handing, like web phones, like smartphones or tablets or iPads or whatever. And what do you think they are doing with this data after they record it? I love these Dynamo charts, and this is already from 2014, so it's probably already outdated. But you can see what's happening online every minute of the day. So in every 60 seconds, what's really happening over there. And you can see that on Instagram, user posts 216,000 photos every minute. There's around 300,000 tweets every minute. There's 350 photos shared on WhatsApp every minute. On Facebook, there's more than, let's say, 2.5 million of user shares. On Google, some people execute over 4 million of searches. And finally, the oldest way of communicating online, email, there's more than 204 million of emails being sent every minute. So you can see the scale. You can see how the modern internet is working and what it actually means to handle big data. And CSC, so Computer Sciences Corporation, they basically say that the data production will be 44 times bigger in 2020 than it was in 2009. So you can already see that it's going up very, very rapidly, and it's not the end of producing data. So what it actually means for Facebook. It's also really difficult to get these data because they don't publish it like, that frequently, and it's not really summarized. But what I've managed to find is that they have more than 1 billion of daily active users, and this is from April 2015, so it's probably pretty recent. They also have around 600 of terabytes of data being, asynchronously replicated between data centers. They have more than 300 petabytes of data in total, and this is from April 2014, so it's probably already like 400 or 500 petabytes. But the most important thing that we want to have a look today is that they are handling billions of queries per second. So they are not saying how many billions of queries per second they are handling, but it's more than it's more than 1 billion, and it's already like such a huge scale that you can imagine how difficult it is to implement a system that does it properly. So we've seen the volume. The volume is really huge, but what are the other V's of big data, and what are the main characteristics of big data that you want to have a look at? Volume was one of them. The other one is velocity. So the speed of generation and the rate of processing is humongous. It's really enormous, and it's increasing all the time too. The other thing is that there's a wide variety of data. So, the data are unstructured or semi-structured, or the structure is ending or, changing all the time. So, it's not like this that we have a structured data that's being handled in the same way all the time. And the last thing is the veracity. So it's not like this that we may, pre-process the data most of the time. The data is untrusted. It comes from various sources. We cannot trust the sources. And, pretty often the data is uncleansed. So we are not normalizing the data. We are basically handling the data as it comes to our system. So the question is now, and this is the core question of this talk. So can RDBMS, so the Relational Database Management System, can they handle such a scale? When we talk about such a scale, is it really possible to take normal RDBMS systems and handle it? So in order to answer this question, we've already seen the characteristics of big data. And let us have a quick look in 2 slides what it actually means to use an RDBMS system. So you're all probably really familiar with it. There's the relational model. We design it up front. We have to know what kind of data we're going to be handling, what we're going to saving and storing in our database. We have to design the tables. We have to design the relationships. And when we create this schema, we can start using it. But it's very rarely. You do not change the schema, let's say, every day or 10 times a day. You normally, when you have to change the schema, you have to do some migration. You have to think, how this data can be handled in a different way. It's a long procedure. You create some data migration scripts, and then you change your schema. So it's not like this that we may, have semi-structured or unstructured data stored in our relational model. The other thing is that, you all know ACID, so atomicity, consistency, isolation, and durability. These are the core design principles that are there in our databases. So if we use a transaction, we know that it's going to be atomic. We know that the data will be consistent. We also know that when we choose a proper isolation level, it's going to be isolated. And finally, when we commit the transaction, we know that it's immediately durable. So when I ask after committing a transaction and I execute a query in a database, I'm sure the data is already there. So these are the main characteristics. And what problems can we actually, expect while using this ACID RDBMS enabled systems while trying to handle this scale of data that we've already seen? So the first problem that we can probably foresee is that, in order to handle such a big traffic, we need to scale. Everybody says that, we need to scale. So how to scale? Normally in RDBMS, we scale up. So we add some CPUs, or we add some new disks, we add some cores. Maybe we, in the shelf, in the server room, you can put some new servers, but still, it's always scaling up. And it's very difficult to scale up to such a level of big data that we have to handle. And in order to, let's say, store more data and to store more data that we can handle while we want to scale up, we have to scale out. And what does it mean to scale out? It means that we have more servers. They are distributed. Normally, they are community servers, which means it's not really like, very high-end server hardware. It's just, normal servers that you can have from a cloud provider or stuff like this. And in order to, to save such a big amount of data, we need more servers. So scaling out means that we store some data in one server, on the one server, and we store some data on the other server. But these are not really the same, it's not the same data. The other problem is that, as we mentioned, as we are doing this sharding and partitioning, so we store these, different data on different servers. How do we really want to do distributed joins? Because as Acid said, we have this referential integrity. So let's say if I'm selecting some data from the left server, and I want to select some data from the other server, and as you can see, in this chart, some data is on the upper server and some data is on the lower server. How do we really want to execute distributed joins? It's obvious that it's gonna be taking forever because of the latency, because for every record I would have to check, okay, are there other records on other servers that are using the same ID so that my referential integrity condition is fulfilled? The next problem that we're probably gonna we have to handle is our distributed transactions. So in order to scale, we said, we have to have more servers, and one of the core design principles of RDBMS are transactions. So let's say I have 2 nodes or 3 nodes, as in this chart. You can see that the distributed transaction is already, sending, the manager has to send a lot of messages to handle, everything out of the box as just one piece. And let's say if we had 100 servers, or if we had 1,000 servers, or 10,000 servers, and we wanted to execute and distribute transactions, would it really scale? Would it scale that we hold the lock as normally like the RDBMS system does for the duration of the whole transaction? It's going to also be taking ages due to the distances and due to the fact that you have to coordinate more than 3 servers that are presented in this picture. So we can already see there's a couple of flaws that are there in the RDBMS systems that we really have to think through in order to handle such a big amount of data that we've seen. The next thing is replication. So, okay, we also want to be operating at a high availability, which means that, it's obvious that some servers will go down. And in order to handle the situation that we are not losing data, we have to have some replication. So again, transactions, distributed transactions, and referential integrity in RDBMS. If we want to do the online replication, meaning that I'm opening a transaction, I'm modifying some data, and I'm committing this transaction, and when the transaction manager returns a message to me saying, okay, your transaction is committed, all the nodes have to be already in a consistent state and have to consist of the data that I have just changed. It means that we're going to have a high latency because we will have to wait till all the servers synchronize before the transaction returns, which of course, takes a lot of time in our case. The other thing is that we can have post-write replication, but it means that we're going to handle some trade-offs because, because it will also take time before the data will be replicated to the other servers. So if I connect to the other server and the data hasn't been replicated, I'm not going to see the newest data. The data will be stale. And the last thing, the CAP theorem that we have to mention, consistency, availability, and partition tolerance. So who can tell me, this is a question, a real question for a mag, how many of them can we choose at once? 2. Raise your hands, I forgot to say. Yes, there. And the right answer is 2, exactly. You can take your mark. Okay, so consistency, availability, and partition tolerance. So consistency means that all the clients see the current data regardless of the updates or deletes. Availability means that the system continues to operate as expected, even if there are failures. So if the nodes go down, we still can operate and we can store and read data. And the last thing is the partition tolerance. So it means that the system continues to operate as expected despite the network or message failures. So even though the messages or that will not reach the final destinations and will not reach the servers that we're going to send them to, the system still can operate, and then the data will be correct. So we can go to we can basically conclude the theoretical part, saying that there's the amount of big data that we have to handle is enormous. The RDBMS systems totally suck because they are not really made to handle such traffic. We've already seen a couple of problems with this ACID referential integrity, distributed transactions. There's no inbuilt sharding. The replication will take forever. And basically, we have to forget about the RDBMS systems in order to handle such stuff. Now, the second question for Riak. Who can tell me what kind of database system Facebook is using to store the social graph? Hands up. Hands up. I don't see hands. Oh, there. Exactly, here. Yeah, you. What kind of system they're using? No, wrong answer. There, over there, on the right. MySQL. Exactly, MySQL. So wait. What's happening? We just said that RDBMS totally suck. We just said, we cannot handle such a traffic. And how is it possible that Facebook is using MySQL? Yeah, basically what they did is they started experimenting with Cassandra. They started Cassandra project. It was probably, I don't know, something 2007, 2008. But at the end of the day, they decided, okay, we don't need this stuff. We're going to take MySQL and we're going to use it as a NoSQL database, because it's all about, all about the fact how you use the database. So what they said is, we will not use joins or large scans. We are going to not do it because it's going to take forever, as we've already presented. They also said that, we will not really favor consistency or atomicity. For us, it's important to read and write. So we have to read and write quickly, because it doesn't matter, if I post something to my timeline and, two friends, one of them will see it in a minute and the second one will see it in 2 minutes. It doesn't really make any difference. The most important thing is that, when I post and I click send, I can write it to a database. And what happens in the background doesn't really matter. Exactly, and also they also favor, asynchronous replication. So they are not doing any online replication, which means they have this eventual consistency that I've just mentioned. They also said, as we said, distributed transactions will take forever. It's going to be, they will lower the throughput and the latency will be high. So they said, okay, we'll not really do any multi-shard transactions. It's just prohibited. When we store some data, it's going to be grouped there, and we will not be really referencing other servers. So exactly, the social graph, it's a really cool system. You can read about it. It's called TAO, T-A-O, and they use MySQL, and they use memcache on the top of it to have some caching layer. There's a lot of articles about it, and yeah, I encourage you to have a look at it, because it's just, yeah, the scale they are handling, as we've seen, it's really huge, and it's a very interesting project. So, as a consequence, we are pranked. We still may use RDBMS systems. So all the buzzwords, that we've seen from all these NoSQL providers that say, when you have to scale, you have to use our product, and all the other products suck. It's not true. It's about the design principles that we are using while we are designing our systems. And we can take RDBMS system, and if we use it in a proper way, we can achieve the same throughput or the same latency values as, as if you were using NoSQL databases. But what's so special about the NoSQL databases? The thing is that they have some other design principles, so we don't have to overcome, problems like sharding or ACID in order to make them scale. They have it inbuilt, so it's their core functionality to enable us, to scale, to add some servers, to do the sharding, to do replication, and stuff like this. And now, what we want to do is we want to have a look at these NoSQL databases to see what kind of mechanism they have inbuilt there to enable us, to handle such traffic as we want to handle. So this is the CAP theorem, but now we can see some databases saying that which database fulfills which requirements. Normally, as said, they have two. So we're going to look at the CP databases, and then we're going to look at the AP databases. So the title is 10 NoSQL databases. We're going to probably cover 4 or 5, but looking at this list, the other ones are pretty similar. They operate in a similar way. So you can, at the end of the talk, you can add some around 10 databases to your CV. Okay, so the first one is called Redis. How many of you are familiar with Redis? Hands up. Yeah. couple of people. So it's a key value store, or what they prefer to call it is a data structure server. It operates fully in memory. So we can also persist on disk, but the main mode is like an in-memory mode. It's very simple. It's very basic, like, the stuff that they are providing is basic, but it's extremely fast. It's really blazingly fast. And what's really, interesting, I encourage you to have a look at the architecture. It's single-threaded. So what they say, when I run a Redis server, there's a single thread that's processing my request. And what they say, that the upper bound is never the CPU, because you have so much I/O, you have so much of other operations that you have to execute that the CPU will never really reach 100%. So have a look at their architecture. What their data structures you can store there, so that you can have a gist how you can use it. There are some simple strings, there are some lists, there are sets. You can use sorted sets. There's also some hashes, so like maps, string to string, and some more complex stuff like bitmaps and hyperlog logs that you can explore by yourself at home. On the right side, you can see how you really operate Redis, how you store data, how you get data. So it's a really, really simple set, get, add, or a couple of other keywords that you can use to store your data. It's pretty basic, but it's extremely fast and very functional. Now, coming to the topic of big data and replication. So how do they really do replication? It's also inbuilt as a core design principle of Redis. You have a master-slave replication. It's asynchronous. And what's really cool here is that it's non-blocking on master and it's non-blocking on slave. So you can basically handle all your traffic while the replication is happening there. And as said, it's like the CP, consistency and partition tolerant server. So it's consistent. So when I read from master, it's going to be always consistent. So when I write to master and read from master, the data set that I'm going to be getting is always consistent. But it's really difficult to say what kind of characteristics of the CAP theorem the databases are really fulfilling, because they are adding some features in order to push the decision on our side. Even in Redis, even though it's initially like a CP server, I can have eventual consistency when I read from the slaves. So I cannot write to the slaves. It's forbidden to write to the slaves because the replication is going from the master to the slave. But if I want to have eventual consistency, I don't care that I'm going to read some stale data. I can read from the slave and have this eventual consistency during my reads too. Sharding. So we've covered replication, now sharding. So of course, to handle this big amount of data, we have to store and distribute the data equally to all the servers. So they implemented it just recently, I think a couple of months ago. It's still maybe not really, really super fully mature, but it's working. So all the nodes are connected to each other. They have some binary protocol among all the nodes, and so it's called ping pong, a really cool name, and also gossiping between the servers. So gossiping means that one server is telling the other server something about the third server. So even though they are not speaking always directly to each other, they're going to get the information about the topology. But what's really important here is that the nodes do not proxy queries. So if I'm a client and I'm going to read something from Redis and I'm connect here, but it turns out that because of the sharding, my data is stored here, the query will not be proxied. I have to ask this server to get this data. We're going to see it in the next slide. So this is already showing the sharding and replication together. But as you can see, with sharding, some data 180 are here, some data 2, 3, 4 are here, and the rest of the data is here. And yeah, in this case, we have replication and sharding. So I have master-slave architecture here among the shards in this silos, and I have a master-slave here, and stuff like this. So when I want to basically get number 7, and I'm a dummy client, and I connect to this server, I have two options. One, I say here, get 7. It's going to tell me, oh, no, this data is not here, it's here. So I have to connect here and get the data. But smart clients, they can get cluster hints. Cluster hints, because we are using like consistent hashing, and how the data are distributed on the servers, it's like foreseeable. So I can just say, OK, from where can I get this hash? From where can I get, let's say, data number 7? It's going to tell me, oh, it's here. So I'm doing some kind of client-side query routing, and I'm connecting here to get the data. So as you can see, it's pretty small, but our architecture is really functional and really sophisticated. I have master-slave replication, and I can combine it with sharding, like automatic out-of-the-box sharding. So I don't have to, do the data distribution by myself, as Facebook had to do with MySQL. When I want to store data, it's going to be stored among the nodes, and I don't really have to care how the data are distributed. So use cases for Redis. Yeah, like it's in memory. It's very simple. It's like a key value data store, as we've seen. So it's very cool if you, let's say, want to show people use it to show latest items in your web shop. If you're adding some stuff, or if people are buying some stuff, you just send a very quick message, fire and forget, to Redis to update the statistics. It doesn't really matter if it's going to be consistent, because I don't care, if the statistics are 100% accurate. If I'm on Amazon and I want to show like the most popular items in the last 4 hours, it's not really that important if it's going to be, if it's going to include all the transactions that have been executed. It's also really cool. It can do pub/sub for you. So publish and subscribe. It also can do queues, like the blocking queues in Java. And what's really cool here is you can block on many queues. So in Java, I can block on one queue, let's say with a timeout. And then if I want to ask another queue, I have to ask another queue. And here I can block on a couple of queues. And some data will be added to the queue. I'm gonna get this data. The last thing, caching, or also a cool thing, expires on time. We've seen like one of the operation was using expire command. So I can insert some data with the expiration, like time to live, sequence, and it will expire after the given time sequence. Okay, so Redis was the first server. As we can see, it's initially consistent and partition tolerant. It's here. Now, and it's blue. All the blue things are key value stores. So if you want to have a look at other key value stores, you can explore the other ones. Now we're going to move to the MongoDB. MongoDB is also a consistent CP database, and it's document oriented. So it's not a simple key value store. It's document oriented. And what is the difference? Because somebody can say, yeah, I'm also storing like a document, and I'm giving an ID, and I'm just storing it. And when I fetch this document from the database, I'm going to get like a big blob, like a big string or big JSON string or whatever. I can do the same thing with Mongo, and I can do the same thing with Redis, as it's also, I'm giving an ID, and I'm storing it in the database. Yeah, that's true. That's a very good point. But Mongo can understand, the structure of the document. So we are storing JSON there, and so I can execute some queries saying, oh, as I'm inserting the data as JSON, I can execute queries saying, oh, I want everything that has an age bigger than 30. So it's storing it as a big document, but it understands the aggregation, it understands the structure that you are storing there. Although there's no schema, so let's say the schema is dynamic. The only thing that I have in Mongo, I have a collection. So I can store stuff in the collection. I say, okay, I'm storing this document in this collection, and it doesn't really matter what the document looks like. It's kind of course, you can store anything, and probably there are cases when you have a collection and you store anything that you want to store there. But what normally people do is it's called like implicit schemas, that I store pretty similar documents in a collection, because if I want to execute a query on it, I want to be able to query it. I want similar data in the same collection. Exactly, I was talking about this querying mechanism. I can use like query criteria, pretty similar to SQL, but it's not, it's not the standard query language. There's no transactions over many documents. So if I store document, it's just atomic on single document. So if I'm executing any operation on a document, it's going to be atomic. But if I want to touch a couple of documents, you will not have an atomic operation on a couple of documents. And you may say, yeah, it probably sucks because, in SQL, I have this relations. I have, let's say, one-to-many relation. I can update all the children of the father node, and, it's going to be atomic. Yes, that's true, but it's pretty similar in Mongo because you have to think about the data in a different way. In Mongo, you are storing one blob, but it's an aggregation already. So I can have this father-child relationship in my document. I can have a client, and I can have all the items that the client has purchased in the document. So in database, in a relational database, I would have to touch a couple of rows to update all the items purchased by the client. In Mongo, I'm updating one document. So it's not that obvious. But you still can do a lot of operations on multiple data if they are stored in a single document. And it's just up to you how you design your data in order to be able to modify them. And and then the modeling is proper for your use case. What other things are interesting for us when we speak about Mongo when it comes to handling big data? So they have also like a replication. It's called primary, secondary, so it's kind of master-slave. We can write to primary only, but we can read from secondary. So it's the same thing as in Redis. If I'm reading from primary, my reads will be strictly consistent as it's a CP database. But if I'm reading from secondary, I can connect to secondary for load balancing of the traffic. But then I have to, I have to be aware of the fact that there's latency. It's not a strictly consistent replication. It's not online replication, so I'll have eventual consistency. I may read stale data from the secondary. And of course, there's automatic failover. If one of the nodes goes down, I have another node that's going to take over the automatic failover thing. Okie dokie, so we've seen replication, but what we're also going to do, we also want to shard. We've seen how it's possible in Redis, and Mongo handles it in a bit different way. So we've seen in Redis that we had to get these cluster hints, or we could be a dummy client and ask one node, and it would tell us where the data is. Mongo handles it in a different way. There are configuration servers. In production, they normally recommend 3 configuration servers, and there are routers. So if the data is sharded, some replica set is here and some replica set is here, I'm using the routers that will connect the configuration servers. It will cache this data so it doesn't have to ping the configuration server all the time, and it will route the query to the proper shard. So we have 3 entities here. We have a router that basically routes all our queries to the proper shard, so I don't have to handle it by myself. I'm just saying the router, please, Mr. Router, give me data with the ID number 1. And the router will do all the things backstage. It will contact the config server, it will store this data, cache this data, and it will connect the shard. There are some more sophisticated mechanisms that we didn't have in Redis. So we are going towards the more sophisticated databases, and there will be some stuff being added all the time in our slides. And we'll end up with Cassandra that has the most of these mechanisms implemented. So we have a read preference. So when I'm the client, I'm using the Mongo driver and I'm asking, I can specify the read preference. I can say, OK, I always want to ask the primary. So it's certain I'm going to get the most recent data and always consistent data. But I can also say, I'm preferring primary, but I can handle stale data just, in order to boost up the throughput or latency. It doesn't matter for me. I can always say, oh, I don't want to, generate bus on the primary server because I'm just generating some statistics. And, doing the statistics generation, I don't care, if I have, like the mostly consistent and mostly accurate data set. I'm asking secondary on secondary preferred, or also for the smallest latency, for the lowest latency, I can always ask the nearest server. So this is a pretty cool option. As said, it gives you more flexibility, and you can decide whether you want to have eventually consistent data and the slowest latency, or like the lowest latency, or if you want to have the strictly consistent data, but you are aware of the fact that in order to contact all the primary servers, it's going to take time. And it's pretty similar with the write concern. So, if you are implementing an application that is writing a lot of data and you have to write with a very low latency, you cannot wait. You can just store in a way that's called, unacknowledged. It's basically fire and forget. So you are contacting the driver. You're saying, hey, Mr. Driver, I'm storing this small JSON document. And, and I'm forgetting about the operation, so I have no guarantee whatsoever what happened with the data. The other thing is acknowledged. So the data has been acquired by the Mongo process, and it has been applied to the memory. So it wasn't written to the disk, but it was applied to the memory. So if the node goes down and hasn't written into a journal yet, I can lose the data, but still it gives me some more security. And the slowest one, of course, but the most secure one, and the one that will give you a strictly consistent operation, is called journaled. So it means that I'm getting the data, Mongo process receives them, applies them to the in-memory data set, and also write them to the journal on disk, and it sends me the response. So this is going to be the longest operation, but if I'm really making this trade-off that I don't care about latency, but I care about consistency, I just use the journaled mode write concern. Yep, so this is MongoDB. It's a bit different from Redis. We've seen there's some more mechanisms that enable us to make some trade-offs. It's a document-oriented data store. So normally people, it's like a hype also right now that people use it for a web-based application, but it really fits well if, let's say, if you are using some modern JavaScript frameworks and you are handling JSON anyway, so then you can use it easily for your as a database for web apps. So, for example, eBay, they are claiming that they are using it for the metadata storage. So all of the servers, all of the information about metadata in their server rooms is stored in Mongo. Also for cloud management, so for their clouds and merchandising categorization. So on eBay, they use it pretty heavily. Also the Weather Channel, a pretty popular website. They use Mongo for this PubSub thing. You can subscribe in your smartphone for weather alerts, and it's gonna do it's gonna send you the notifications whenever a new alert is being generated in your area. Yep, so we've seen two databases. Both of them were from the CP category initially. One of them was Redis, the second one was MongoDB, and now we're going to move forward, but we're going to stay in the CP category. We're going to go to HBase, which is a data store that can give us something new, something different. So we've seen a key value store, we've seen a document-oriented store, and now we're going to see a big table store. So the initial story began with Google. They've created this big table project that was based on Google file system, and then open source implementation followed. It is called HBase, and it is implemented on the Hadoop file system. It's a data store that's column-oriented, so we haven't seen a column-oriented database yet. But it's a bit different than the columns that we know from the relational database. We're going to try to cover it a bit later. It's strongly consistent when it comes to read and write operations, and what is really cool, it also enables us to do the automatic sharding. So we don't have to, while we store the data in our big table, we don't care, on which how we shard this data. It's going to be done out of the box by HBase. So what does it actually mean to be a column family data store or column family oriented? Normally, it's similar to relational databases, but it's different. Normally, when you have a relational database and we have a table, all the data are stored in rows. So I have a row of data, I have a couple of columns, and the rows are stored, like at once. So I have a row, then I have a second row, I have the third row, and when I'm reading the data, I read them row by row. So even if let's say if I have a table with 20 columns, and I'm doing select one column from all the data set, I have to read all the rows by row to get all the data that, even though I want to select one column in a bit simplified way. With a column family store, we are storing the data as column families. So you could see this in the previous slide. We have an ID. There's no referential integrity, so I'm just storing this with customer ID 101, and I'm also storing this thing with the customer ID 101. But these are column families, meaning that I optimize how I store the data for my use case. Because let's say I'm always selecting name and city in order to present it in a table somewhere in my web application or whatever. And in the other view of my application, in the other use case, I have to, by ID, I have to get what they have recently bought. So these data is stored, at the same location. So in order to, scan all the rows, in order to scan all the data, I'm just fetching this column family. So I don't have to fetch all the data in order to get these 2 columns. I'm fetching the column family, which really optimizes my storage and optimizes how the data are physically located on the Hadoop file system. So I encourage you to read something more about this column orientation. There's a really cool book by Martin Fowler. It's called NoSQL Distilled or something like this, and it describes this in detail. It's a very interesting concept. But for now, what we have to remember right now is that it offers these columns. It's a bit different thing. We store data in column families. We design the column families that are just tailored for our use case. And it also, it supports wide and sparse tables. So it's easy, like for example, in Cassandra or in HBase, I can have 10,000 columns because every column is a new element in my list. So it's not a problem. If there's no data in a column, it doesn't take any space on our disk. So I can have really wide and sparse columns, where only a couple of cells are full and other ones are empty. So as normally, we are looking at replication and sharding. In HBase, sharding is done by regions. So the table is divided into regions. If they see that the table is being filled with data, the region may be reassigned, the table may be rebalanced, and some data may be moved in order to fulfill the requirements that we specify. So we can see here that it's like a logical view of a table A, and we can see there's the first region, there's the second region, third region, and fourth region, and you can see that the data is being evenly distributed on some region servers. These are physical servers, and if I'm fetching the data, I'm fetching the data from the region transparently. How is it implemented? There's this master node, so to say, that assigns the region, and it also, it knows what data is stored where. It's doing the load balancing also, and it's responsible for the failover. So there's a master node, and we can see the master node here. And also there are these region servers that are, responsible for managing the regions that the master is assigning to them. They can also split the regions, so they say, okay, we're splitting the region, so they are dividing data in 2. And also, so the region servers are responsible for the real I/O operations of reading and writing data. So this is a totally different concept as we've seen the other databases. Here it's working in a different way. We have these master nodes and the transparent regions. And how does it really look? And we're not going to really go into much detail here, but there's also Zookeeper that's responsible for keeping all the configuration. We're going to omit it here. I encourage you to read something more about it. But what I'm doing is, where is the master meta stuff? It's server 2. And then I'm going directly to server 2. I'm fetching my data. These are these H files in the Hadoop file system, or the data is coming from memory, and I'm getting the data for the client. So it's also a pretty it's not really like a seamless process because I have to check some stuff. Where is the meta server? Then I'm going to the right region server. But it's how it works with HBase. Write is pretty similar, so we're not going to really cover this due to time limitations. What about replication? So as said, we have this automatic sharding. This big table is divided into some regions. And but what about replication? We want to be highly available. So if some data, if a server goes down, we want to be sure that the data is still there. And we have also async replication. So the data, even though the primary region server for this key is this one, the data is going to be asynchronously replicated to the second region server. So if this server dies, I can fetch the data from this server. And the mechanism is pretty similar. We've seen 3 databases already, Redis, Mongo, and HBase, and it works the same way. So in order to be strictly consistent, I read from the primary region. But also, if I want to get some stale data or eventually consistent data, I can go to the secondary server and read only from the secondary server. So this replication is also done out of the box. Is a mechanism that's inbuilt in HBase, and you can start using it right away. And as said, it's a new feature. There are two companies who are actually like commercial companies behind HBase that are using it and pushing it forward and implementing it, commercial projects using it. One of them is called Cloudera, and the second one is Hortonworks. And Hortonworks put a lot of effort into this. I think it was released somewhere January, February 2015. We have some consistency level that we can specify while we are doing some read on writes. And normally it was a strongly consistent operation. So I was always going to with the write operation to the primary region. But from now on, from the newest versions, I can specify a timeline, consistency, which means that I can also, it's called timeline, but it basically means that I can go to the secondary regions with my operation in order to load balance the traffic, but being aware that the data I'm going to get or write may be stale. So use cases. For HBase, basically Facebook claims that are using it. So we've seen Facebook uses MySQL and Memcache for the social graph. They are using HBase for messaging. So if you send messaging from one user to the other user, they are using HBase. It's basically, if you are doing some high write throughput operations or low latency random reads, and you need like a wide sparse table, you can use HBase. Also strongly consistent data store. So if you need strongly consistent operations, you can use HBase, and it's going to work for you. But right now, with the timeline consistency, I can also execute operations that will deliver data that with the guarantee of eventual consistency. Yep. So we've covered 3 databases. Now we're going to move forward to the last data store, or second to last. So what all the databases that we've just seen have in common? There's one characteristic that hasn't changed, and it is that everything operates in a master-slave mode. So if we have a replication, we always have this master node, and we always have the slave nodes that we can't write to, but we can read from with this eventual consistency warranty. The Dynamo storage, it was a paper produced by Amazon. So Google produced a paper about this Google's big table, and basically in the same time, somewhere 2007 and 2009, Amazon also operated at a huge scale, of course, and they had to create something that fits their requirements, and they published this Dynamo storage paper. And what they basically say is that, we don't want this master-slave stuff. We want just a ring or of nodes that they have the same responsibility. So we want data partitioned using consistent hashing. We want the data being partitioned and sharded among the nodes, but there's no master slave. We want to be able to add some new nodes to handle some new data, and everything has to be in a master-master way. When we store the data, we don't really want to update any data. We just want to, store the new version of the data. So when I store some data here, and then I store some data here again with the same ID, I don't really want to look up the stuff, or where is it stored, or what is the value, I'm storing a new value, so I'm updating the value. No, I don't want to do it. I just want to have a high write throughput and with a very low latency. So I just want to, store new versions, and I want to have some kind of object versioning. And I also want to have some more complex stuff that we're going to try to explain later on. So this was a paper, and that kind of tried to put a new dimension to the design of modern data stores. And this is what Cassandra actually took. They've taken this table, big table project by Google and HBase, and they said, okay, this wide column family oriented data store is pretty cool, but we don't want this master-slave stuff. We want to have this Dynamo properties, these Dynamo characteristics in this data store, and they've created Project Cassandra. So Cassandra works basically as a combination of wide column data store with this Dynamo characteristics. So they have this incremental scalability that we're going to speak about later on. Everything is a master-master network. So if I add some new nodes, the data are sharded. We're using consistent hashing, and meaning that if I add some new nodes to the ring of nodes, the performance will scale in a linear way. Also, eventual consistency. And there's tunable consistency is something that is very, very important for Cassandra. It gives you the biggest flexibility whether you want to handle your data in a consistent way using strictly consistent warranties, or whether you want to have stuff that's eventually consistent. And what's really important here, there's no single point of failure. So there's no master node if it goes down. You don't have to be prone to the problem that the master goes down and the slaves are not really in sync with the master. You can operate with such parameters of the operations that you may be sure that all of the data is consistent, even though you are doing operations on multi-shard, couple of nodes operating in the master-master way. So how does it work? It works in such a way that, as said, everything is master-master, and there's a coordinator. So the coordinator is doing query proxying. So if everything is distributed using consistent hashing, so we know basically what data using which key is stored on which node. Every node is responsible for slots of the hash algorithm. And let's say if I'm fetching data that resides here, here, and here, the coordinator, I can ask any node in the ring. It's not, there's no single point of failure. And this node will be my coordinator. So it's going to ask the nodes here, and it will deliver me the data. They may have different versions of the data, but everything's going to be compared using the versions of the objects, and I'm going to get the newest piece of data as a client. So what's really important here? There's a couple of concepts. There's, the write throughput is just amazing with Cassandra, and it works in such a way that we have this division between memory and disk. We have these tables called SS tables. These are tables that are stored on disk, and we have mem tables, which are tables that are in memory. And of course, we have a commit log that's also on the disk. And when we want to store data, we execute the write operation. And this data will go to the commit log, so we are sure to the disk that the data is not lost. But primarily, it's going to go to the mem table, so a memory table. The memory table will not write this data to the SS table during our write operation. These tables are flushed and are stored on the disk, like asynchronously and periodically. So whenever the mem table has a specific size, when I store a lot of data, or a certain period of time expires, this is going to be stored here. And this is an immutable structure. This is a structure that's immutable, so it never may be modified. And this is a very important concept when we look at the read operation. So we've seen I'm always writing the new version, and we can see, okay, a key 1. This is our key that we want to fetch now using our read operation. Here's the key 1. And this SS table have some values. So for example, column 1 has value 4. And here in this SS table, I have a new version of this object because column 1 has value 5. So it's a new version. And whenever I execute the read operation, I'm going to be searching through the SS tables to get all the versions of my records, and then I'm going to get the newest value. In this case, it's this one. This was written later, as this timestamp that we don't see here states. So of course, you may think, okay, it's a disk operation. I'm gonna have to scanning all the files and looking for the data. It's gonna be slow. No, it is not. There's really a lot of sophisticated mechanisms implemented in Cassandra, like Bloom filters and some caches and a lot of cool stuff. So I encourage you to read about this concept a bit more. But this is really, so the crucial characteristic that we can see here is that we are not updating our data. We are always storing a new version of the data, and while we execute the read operation, we merge the data according to the timestamp to give the client the newest record. Okay, and we are moving to the last slides with Cassandra. You can tune your consistency, which means that it's just up to you what kind of consistency you're going to be operating at. Cassandra has a couple of mechanisms. The first one is called consistency level. So let's say if I'm writing the data, I can say I'm writing with consistency level 1. So it means that the data will be written to one node only, and the write operation will return. But also, what Cassandra will do in the background, as the data are also distributed on some other nodes, it will, in the background, it's going to also store the newest version of this node, of this data that I've written on the other nodes, so that if I ask this node, it will have the newest record. After a bit of time with the eventual consistency. But I can tune this with this consistency level. What's also cool is that if I execute a read operation and I'm using consistency level 1, what Cassandra will do in the background, it will fetch the data from one node, but it will also execute some digest queries. Digest query means just send me the hash of the object, and let's compare it with the real value to check if the data is the same, whether these nodes have the newest version of the data. If not, there's going to be a operation that's going to repair the data on the other node. So in the background, Cassandra will try to, keep the newest values, keep the newest data on all the nodes, even though you just read or wrote data using the consistency level of 1. So it gives us a lot of flexibility, and it gives us a lot of, basically a lot of freedom while we operate. Of course, we may say, I can write at a quorum. So let's say I have 3 nodes and I want to write at a quorum. Quorum would be 2 nodes. So basically, I will execute the operation on 2 nodes because I'm going to be choosing the consistency level of a quorum. In this case, from this 3, it's 2. So my operation from the client to the coordinator will not finish. I will not get a confirmation that the operation has finished before the data has been written to the 2 nodes that I've seen here. And so this is something that you basically, as a designer of an application, as you can choose by yourself. And the most important thing here is that you may say, okay, but it's all eventual consistency, so my data will never be strictly consistent. But there's this rule that, let's say, okay, this ring is a very big ring, so we can, let's say we choose these 3 nodes. We choose these 3 nodes, and we say our ring consists of 3 nodes only. There's a path here. And if I write data, let's say write with the consistency level of 2, meaning that I'm going to write the newest data to 2 nodes. Let's say I'm going to write to these 2 nodes. And all the 3 nodes are responsible for storing my hash. From how many nodes do I have to read to be able to be sure that I have written the newest data if I wrote to 2? Hands up if somebody knows the answer. I don't see any hands. No hands? Yeah, so there's this rule that if from 3 nodes, if I wrote the data, save the data on 2 nodes, in order to be sure that I got the newest data, I also have to read from 2. Because if I read from 2, I'm sure that out of 3 that I'm going to read, let's say, from this one, but I will always read also from one of the nodes where I have saved the newest data. So the rule is that the number of nodes that I'm writing to and the number of nodes that I'm reading to has to be bigger than the number of nodes that's responsible for this hash value, for this slot. So if I have 4 nodes and I wrote to 2, and I read from 2, there's a chance that I'm going to read from these 2 which don't have the newest value. So if I write to 2 nodes out of 4, I have to read from 3 nodes in order to be sure that I will always select one of the nodes that have the newest data. This is the rule that basically will guarantee me strict consistency when it comes to read-write operation with Cassandra. So it's a very sophisticated mechanism. It's also really difficult to explain all the details in a couple of slides, but I encourage you to have a look at this database because even to understand what mechanisms are there, to apply these rules to our code while we are using it. There's also a couple of more mechanisms that I don't want to really go into details right now because it will just clutter the view, but hinted handoff read repair and full of incremental repairs are also some nice concepts that I encourage you to explore. So Cassandra is basically definitely the most sophisticated, but also the most advanced and most complex database. It's not really that easy to understand all the concepts right away. It also requires, maybe not basic knowledge or more advanced knowledge when it comes to the how you model your data. in order to, to get most out of the design of this database. So you basically denormalize your data. It's normal that you denormalize your data because otherwise you're going to be falling into the traps that you also could see in the RDBMS systems. So yeah, there's a lot of big companies with a huge scale that are operating Cassandra. Netflix has 2,700 nodes in 4 data centers with 90 clusters. And yeah, they store all the film metadata. They store all the user ratings and also recommendations. So they use it pretty much for most of the stuff that you see on the web page. Yep. So we've covered databases from this area: MongoDB, Redis, and HBase, document-oriented, key-value, and big table, column family-oriented, and we've also covered Cassandra, also column family-oriented, but it's not strictly consistent by its design. It offers you write and read availability because you have this master-master architecture. But if you want to operate at strictly consistent level, you can also do it using the rule that I've just presented. We've got 20 seconds. Yeah, the thing is that, it's not a Swiss Army knife. As said, you can do a lot of stuff with RDBMS systems. You can do a lot of stuff with NoSQL databases. You have to understand what the differences are, but you also have to understand what your use case is and at what scale you're going to operate. Because if you are, storing a couple of gigs and you are saying it's big data, I'm sorry, you are wrong. You have to understand, what your requirements are and how much data you're going to store, what are the throughputs you have to handle, what latency you have to handle, and then you can choose the mechanism that will suit your use case. I've tried to cover like the differentiating factors. I've tried to cover, all the things that differ, and also show you the mechanisms that really enable these databases to operate at a bigger scale than the RDBMS systems. But as proven by Facebook, you can also do it with RDBMS systems if you, follow some design principles. Okay, I think the time is up. If there are any questions, I still have, I think, 3 marks that I haven't given out. So if you have a question, please go for it. Yep, on the left side. Mm-hmm. Mm-hmm. And the question is, what would be the right choice to use the NoSQL database? Mm-hmm. Is there some kind of backup database? Yeah, I think this question is complex, so maybe we can just discuss it afterwards when the session finishes. Any shorter questions here? Yeah. So the question is that I've said that Cassandra doesn't have a single point of failure, but there's a coordinator node. That's a very good question. So every node can be a coordinator. I can connect to any node, and this node will coordinate my queries. So you also get a mark, so you can pick it up afterwards. Okay, the last question. Are there any last questions? Okay, I don't see any hands, so thank you very much.